Great. Well, it's great to be here. I want to thank the conference organizers, particularly Adam. I think we've all really gotten a lot out of this conference, and it's been a great opportunity to be able to both be here and to present. So what we're going to talk about today is an ongoing effort. We've been working on it for a year and a half, 2 years, somewhere in that interval now, to develop formally private mechanisms in order to protect and quantify the privacy loss in the upcoming 2020 Decennial Census. The Decennial Census, as we'll talk about a little bit here, is our flagship product. So it's the one that we are constitutionally mandated both to produce and is sort of our constitutional reason for existence. There are many other census products, and actually Ashwin talked a little bit about some of the others earlier, but this is the one we're focused on. So here's a quick overview of where we plan to go throughout our presentation. First, I'm going to give sort of a broad overview of what Decennial is and some of the algorithms that we've tried, some of the challenges that we've faced. Then William is going to talk about structural zeros, which are a particularly important and somewhat unusual within this literature class of things that we call invariants, which are just quantities that can't change from the original data to the final data. And then lastly, Steve is going to talk about integrating geography, because we have I don't think it's unfair to call it enormous geographic hierarchy, and an enormous sort of level of geographic precision that is expected of the final data that we generate. And then you guys can ask questions or make comments, but you should feel free to do that throughout. It's OK to just interrupt us, particularly me if I'm speaking too quickly, because I will almost certainly do that. OK, so let's move forward a bit here. So as I said before, we are part of a team developing formally private mechanisms to protect privacy in the 2020 Decennial Census. Our goal is for the output to be protected query responses that will eventually be converted to microdata. We'll talk a little bit more about why we're converting it to microdata in a little bit. The privacy guarantee here is we've actually had several conversations just at this conference about this. Maybe the safest way to describe the privacy guarantee is that it's essentially differential privacy conditioned on certain quantities remaining invariant from the original data to the final data. In particular, we can derive an interpretation of that from pufferfish without too much work. It's not that difficult to use the pufferfish framework to come up with a definition that exactly represents what it is we're doing. Just to illustrate some of these invariants we talked about, so there will be the structural zeros when William discusses them, but we also have a number of totals that have to remain the same at the block level in our geographic hierarchy, which will make more sense when Steve talks. But for example, total population in a block, number of householders in a block, and the number of voting age persons in a block are all invariants. So those are numbers that, due to current interpretations of legal requirements on census, we are expected to ensure that those quantities don't change from the original data to the final data. And so the strongest possible sort of differential privacy guarantee that we can provide, or formal privacy guarantee we can provide, has to be conditioned on these quantities essentially being treated as public knowledge. So we sort of have to assume that whatever prior a person comes to look at our final output data with, that prior could potentially include these things, and we may as well assume it does. So one thing we've discovered in our year and a half, 2-year slog working to develop these mechanisms is that, as far as we can tell, the Decennial Census has a number of properties that are not typically addressed in the differential privacy literature. So I'm going to run through a quick list of those here. The first is that the Decennial Census has a very large scale relative to what we've seen in the literature, with a very complex workload. Now, I say this, and this might raise a few eyebrows, because if you actually look at the form itself, the form is not very complicated, and that's something that I think Census has in the past been rather proud of. And it's true that it has fewer variables than a lot of our data products. Relative to something like the ACS, for example, Decennial is sort of a small fish when it comes to just looking at how many variables there are and the dimensionality of those variables, and sort of how many levels you get if you take the naive Cartesian product of the levels of each of those variables. That being said, comparing it to most of what we've seen in the literature, it still seems to generate histograms that are massively larger than we are accustomed to seeing these mechanisms applied to. We also have, so just to elaborate a bit on this complex workload issue, we have both low and high sensitivity queries, where by high sensitivity, I, in sort of a vague way, mean that they may or may not have bounded sensitivity. And if they have bounded sensitivity, the bound is probably not a very good bound unless you think about it rather carefully. We also have multiple unit types. So this gets back to something that one of our collaborators, Ashwin, had brought up earlier, and that also came up, I'm going to screw up the name, but in the talk yesterday about Uber, we have essentially relational data. If we form the flat file corresponding to the problems that we're solving, that flat file would be beyond astronomically large. The only really terse way to express a lot of this stuff is through a bunch of tables that are linked together in some appropriate way. And so in our case, in particular, we have households, group quarters, and persons. And persons generally need to be stuffed into either households or group quarters. So we intend to generate microdata that will have legal integer response values. The definition of legal will be elaborated upon again when we talk about structural zeros a bit more, but it incorporates in particular that they should be non-negative, and that these non-negative values should also respect the invariance we gave previously. The reason that we need microdata is kind of at the end of that last sentence, or that sentence that I just walked through. It's that the system in line after us at Census that has existed for years and years, and that we don't have any ability to say, hey, you have to completely rehaul this because it's making our job somewhat harder. That system that tabulates the actual final tables that constitute the primary data products generated for the decennial census, that system expects to be handed microdata. It doesn't expect to be handed a disconnected set of tables that are equivalent in some informational sense to microdata. And so because of that, microdata is what's expected of us and what we are sort of obligated to produce. We also have this sort of interesting issue that I think others have run into in applied scenarios before as well. There's sort of an evolving / distributed set of evaluation criteria, by which I mean there is no concise list written down anywhere that specifies for us in a clear formal fashion exactly how important each element of our tables is, and compares that importance in some meaningful sense to other queries within the workload that is usually generated. So figuring out how relatively important subsets of our workload are and of the tables that we're generating are is something that we just actively discuss with subject matter experts and try to sort of, through an iterative process, figure out what would help them understand the costs and the trade-offs between the different tables that they've historically been comfortable publishing. So that in itself has been an interesting challenge. And within that challenge, there's sort of this related issue of, for the algorithms team, which we are a subset of, there is this question of how do we ensure that the final algorithm we produce has some sort of manipulable toggle that you can alter in order to say, hey, I care twice as much about this particular subset of the query workload that we're going to finally output. How do I enable the decision makers to be able to control that in a reasonable way? So continuing with our list of problems, the next is the geographic hierarchy, which I alluded to briefly before. It consists of approximately 8 million blocks throughout the United States. There is a hierarchy above the blocks themselves. It runs from nation to state to county, I believe is next, down to tract to block, group to block. I may have left a level out, but I think that's right. And all of those are sort of nested within one another. And that structure itself creates some interesting complications. There's also this issue that we end up, as you move down the geographic hierarchy, we end up with extremely sparse histograms, and we also often start with modestly sparse histograms. So the modest sparsity in the beginning comes from our tables just being extremely large if they're generated in sort of the natural way. The extreme sparsity at the lower levels of geography should be no surprise, because by the time you've gotten down to one of these 8 million blocks, there's often maybe one household in a block, or just 4 or 5 people in a block. At that point, most of your histogram is just 0. So another set of properties that I've mentioned before, but that I think sort of deserve reiteration, are that we have quantities / properties that must remain invariant. This includes structural zeros and also certain marginals over the data. And finally, again, alluded to before, but the data are relational. We have to eventually have people in some way or form in our microdata, their relationship to which household they're in must be represented. And similarly for group quarters. Maybe to elaborate a bit, group quarters consist of things like jails, college dormitories, that sort of thing. Okay, so as mentioned previously, we intend to produce DP microdata, not just DP query answers. The reason for this is that upstream processes expect us to produce microdata, and we can't just say, hey, privacy is important, you have to change how you're doing everything. Microdata have a few other sort of useful attributes as well. I mean, it's not just about this expectation. That's probably the most important reason. But it's also the case that they're familiar to internal domain experts and external stakeholders, which is partially why they were the thing expected by the tabulation system in the first place. They also give us a nice compact representation of query answers. They're convenient for generic data analysis. And of course, they provide consistency between queries run across them just sort of by construction, which is a nice property. Our goal is not for us, the folks on the algorithms team, to make any concrete final decisions about what the budget expenditure should be. The final budget for our epsilon DP algorithms or pufferfish with suitable modifications should be something that's decided by census leadership. So our goal is, on the algorithms team, to try and improve the frontier that represents the accuracy-privacy trade-off. We want to push that to be as nice as it can be. So we want to find the trade-off curve that dominates all the other trade-off curves that we've generated prior to that. And in the final analysis, we want to provide levers or gears that allow leadership to, in some hopefully reasonably intuitive sense, manipulate those toggles and figure out where exactly on that curve they want us to be. So this maybe begins to get into calling it technical is maybe a bit much, but this lists off sort of the algorithms that we've played with, that we've tried, that we've experimented with, or that we have at least in some cases just considered. So of course we have the basic building blocks. We have the Laplace mechanism, the geometric mechanism, and the exponential mechanism. I will say, just sort of as a point of information, that we don't really get to use the Laplace mechanism for anything due to concerns that have been raised, I believe in one of Ilya Yamirov's papers. He was here and speaking earlier today. We don't have access to a suitable crypto library right now internally. Fortunately, that actually hasn't been a major issue because it turns out the geometric mechanism is nicer for most of our applications anyway, so it's sort of okay that we can't really use the Laplace mechanism. But most of our work is focused on the geometric mechanism with the occasional use of the exponential mechanism where appropriate. So more complicated algorithms that are essentially fancy compositions of those and occasionally with some more interesting ideas also incorporated into them. We've looked at a number of binning algorithms, so algorithms like AH partitions, which tries to sort of look at a histogram and break it up into sub-histograms or sub-bins that are relatively constant, and that if they're close to constant, then gives them a nice estimate of what the counts are in each of those levels. We've looked at sort of PrivTree, which is an algorithm based on classical quad trees that have then been privatized appropriately. We actually started our work with multiplicative weights exponential mechanism, but we found that it was very difficult to overcome some of the runtime issues we encountered with it, and also that its error was not competitive for our use case with the algorithms we have ultimately sort of settled upon. And there's a related algorithm called dual query that I just put up there because it almost gave me an excuse to do mixed integer linear programming, which is where my background actually is. But unfortunately, we also ended up not running with it. So iReduct/noise down, which provides some interesting ways of sort of intelligently controlling how much budget we're spending on different queries to account for the magnitude of a particular count, and enable you to do things like target the relative error in a differentially private fashion. We've also looked at the data-aware workload-aware mechanism, which, as the name suggests, has both data-aware and workload-aware components. So it attempts to adapt the algorithm's decisions to the particulars of the query load, the workload that you're trying to target, and it also attempts to do so in such a way that it takes advantage of structural properties in your data. Maybe a theme in a lot of the work we found is that at least for our particular use case, this notion of data-aware algorithms has not really been a particular success. This probably just means that we're hunting for the wrong structure, we're doing it in the wrong way, but most of the work we've looked at, the data-aware component of algorithms has not yielded sufficient improvements in accuracy to justify the cost of finding that structure in the first place. We've looked at PriView, which is a way of sort of nicely generating a large number of marginals of a particular order. And then finally, we get to the algorithms that really form the core of what we're doing right now. There is a variant of the matrix mechanism called globalopt that a number of our academic collaborators, so Jerome, Michael, Hay, and Ashwin, one of whom was supposed to be here, one of whom was here just a bit ago. This globalopt algorithm is an extension of their basic matrix mechanism algorithm that is better optimized for very large-scale workloads. And I think in particular, if I recall, what it attempts to target are workloads that are naturally represented as Kronecker products, which is also a recurring theme in a lot of our mathematics. So most of our workloads can be succinctly represented as not very natural subsets of Kronecker products. And sometimes we don't know quite what the true workload should be, so sometimes we just say, well, maybe this particular Kronecker product is a suitable representation for what our workload is. And then finally, HB-tree. So HB-tree is just a particular algorithm that builds a tree in a differentially private way that has a nice closed form for targeting mean square error over all possible range queries in a single dimension. And we essentially use a large number of HB trees in what we call the hierarchical branching forest. It might be a little bit ostentatious for us to bother giving it a new name because it's literally just copies of HB tree over and over and over again, one for every copy of the remaining dimensions in a particular table. But we found, to our surprise, that this HB forest works incredibly well for most of the workloads we've looked at. It is both exceptionally fast and its error is competitive with everything else that we've looked at, often outcompeting other algorithms. And then, of course, we still have matrix mechanism / global opt. I think our suspicion currently is that global opt will eventually be the algorithm that we actually end up focusing on. The basic idea, for those not familiar, behind matrix mechanism and global opt is that they take your input workload, they kind of look at it and say, well, this workload is nice, but it has a lot of correlation between some of the queries, and that's pushing up the sensitivity of the workload. Maybe we don't want to answer this workload directly. We should instead transform it into some other workload. This other workload now has some nice way of inverting it to get the original answers to the original queries we're actually interested in, but it has a lower error ultimately. And there's a nice closed form for what the MSE looks like in that case. So I think we expect we'll end up going with global op in the end. A key point to note is that nothing that I've talked about so far gracefully handles DP joins. So this issue I alluded to previously of the relational database nature, or the relational nature of our databases is still a major sort of shadow behind us. So after the DP algorithms have been implemented, so most of our work actually proceeds in 2 phases. We have a bunch of DP work that's done, and then in order to incorporate all these invariants that we've talked about, we have a number of post-processing algorithms that are implemented and applied. So these post-processing algorithms, we've also tried a number of approaches. Originally, just sort of a naive approach, we attempted doing some weighted averaging plus mean consistency, which is a particular post-processing sort of little trick that is embedded in the original HB tree paper / ordinary least squares. There are a number of problems here. So it is nice that it gives closed form in an a priori sense for something like mean square error, but it doesn't give us integer counts, doesn't give us non-negativity, doesn't incorporate invariance. It is fast with a small memory print, but when the answer is completely wrong, that doesn't really do us a whole lot of good. So another option that we considered were sort of quadratic programming to implement non-negative least squares algorithms. Here we sort of lose that nice closed form a priori for accuracy. We still, of course, get an error in the end in terms of the objective function, but it's harder to optimize in a general sense over the parameter space. But again, we don't get integer counts. We have a number of scaling issues with the optimizers we've looked at. You can see the quick list of some of the optimizers we've investigated. We also found originally that there's some care has to be taken to avoid small, consistent positive biases being introduced, but with this non-negative least squares approach, turning into dramatic positive biases when you look over marginals over a number of dimensions. So that was another problem. We sort of have addressed that mostly through modifications to the objective function. Again, and this also only incorporates certain invariants. In particular, it fails to give us integer counts. Finally, it's fast with a small memory footprint. And there aren't arbitrary linear constraints here, although I'm sort of splitting hairs there. Next, we've considered mixed integer linear programming, partially just because that's where my background is, and so I really wanted to talk about it. But it won't work because it simply can't scale to our use case. If we're having trouble scaling something like non-negative least squares, there is zero hope that mixed integer linear programming is going to be even remotely performant. So finally, this is kind of where we've currently settled for most of our post-processing work. It's a combination of quadratic programming and general linear programming, slash a technique called iterative proportional fitting, which I am somewhat less familiar with, but I'm happy to attempt to answer questions on anyway. So once again, we don't have this nice closed form, but I think we've kind of given up at this point on having that nice closed form a priori, so we're not really worrying about that so much. We do get integer counts because with this Kronecker product representation of the queries that we've started working with, we can show that for natural classes of linear programming problems, we get total unimodularity, which is an important property in the sense that it means you can solve a linear program using either a particular simplex algorithm or a barrier algorithm with a crossover step to make sure that you get to a vertex of the polyhedron you're wandering around, and you're guaranteed that the solution at that corner of the polyhedron will be integer valued. There are some technical conditions there that I'm hand-waving a little bit, but in short, we can get integer values in a sort of scalable way if you forget that the histogram is also exponentially sized in the number of variables. So it gives us non-negativity. It incorporates most of our invariants. The reason there is a most here is that the total unimodularity property is lost when we try to simultaneously combine units of different kinds. So if we incorporate households and persons, all of a sudden we can't get integers anymore, or we have to do something heuristic rather than optimal. Finally, it's fast with a small memory footprint, but as I kind of alluded to before, we're still pretty bottlenecked by large histograms because the histogram itself is dramatically large. And so using a fast algorithm on an exponentially sized input set is not necessarily going to be a fast thing. Again, as with the DP algorithms, none of these methods gracefully handle post-processing joins. This is sort of related to what I just said about total unimodularity. Nope, go ahead.
Slow down and,
Yep.
and say a little more about that. So what do you mean by sort of what's an example of a post-processing join you'd want to do in this context?
So ultimately, the final microdata that we generate, it could take any of a number of forms, but presumably there should be a list of households and there should be a list of persons, both of which should be DP. And we would like some way to figure out which households these people belong to. And so that's kind of the join we're referring to.
I see. So what you want is to synthesize data that preserve sort of joint statistics of these tables.
Right, exactly. As well as the statistics considering the two tables separately.
Right. But when you say post-processing join, so one approach, I guess, would be to add the joint statistics you hoped would be preserved to the set of things you want to, your first differentially private mechanism outputs,
right.
And then try to fit, the pair of tables at the same time to the noisy outputs. And you're saying that's just not feasible computationally, or?
Computationally, it's possible we could scale up to do that with a few sort of heuristic step arounds. The real issue there is that if we have household level DP estimates and we have person level DP estimates, then this total unimodularity property that we're dependent upon in order to do any reasonable scaling and still get integer values for our microdata completely falls apart. We could give up on that, but getting integer values that satisfy all of our exact constraints simultaneously is itself hard. So it's not like we can just round things and be okay either. Is that kind of beginning to get your question, Adam?
When you get non-integral values for the microdata, are you essentially getting sort of like a distribution over data points? Rather
you can think of it that way, yeah.
A finite set?
Right.
And is that such a bad thing?
It is a bad thing in the sense that we will not be allowed to feed that into the tabulation system if the counts are incorrect. So the exact constraint requirements are in fact exact. If there's any deviation whatsoever from representing microdata exactly and representing the exact constraints exactly, I'm not really sure what the ramifications of that would be other than that we would be censured, I think. And the process might stop at that point. We may not be able to feed the microdata downstream. We may be asked to redo things, at which point we'd be back to the original technical problem. Is that good?
Yeah, no, I think that answers part of my question. Yeah, that's great. Thank you.
So instead of post-processing the data to ensure consistency, have you thought about any ways to maybe incorporate the constraints into the actual differentially private sampling mechanism?
So we have discussed it a bit. We haven't gotten very far with anything that seems like we have time to actually attempt to produce it. The closest that I've come is there are cutting plane algorithms in the linear programming literature, and as you add each of those cuts, you can think of it as something that can be differentially private. That algorithm ultimately, when you start to think about it a little bit more, ends up looking very much like an L1 version of MWEM. And since we didn't have much success with MWEM, I'm not sure we'd have much success there. It's also possible you could attempt, so the reason I'm focusing on this linear programming focus is because I want to make sure we can still get integer values at the end that are consistent with all of our constraints. Something else you could do is attempt to sort of directly make the simplex algorithm differentially private, but I think that is beyond our current resources and sort of the time horizon we have available to us. There are a few techniques. So I know Dan Kiefer was the technical lead for the project for most of its lifetime, and is still sort of in spirit the technical lead of the project. I know he came up with a reasonable way of, it's still sort of post-processing, not really DP, but maybe it would be more amenable to being made differentially private, with a conditional distribution that was nice and relatively easy to sample from and would respect, I think, just the one total population constraint. But we had issues when we tried to simultaneously account for multiple of the exact constraints and the integrality at the same time. And with that, I think it's time for me to hand it off to my colleague, William.
Okay, yeah, so I'm going to go into a little bit more detail of some of the things that Phil alluded to, and hopefully convince you that the problem that we're working on is a challenging, complicated one, but ideally maybe you'll come back and say, actually, there's a very easy way of doing this, which we would love. So I'm going to talk a little bit about like the census data products that we actually need to ultimately produce. And some of the dimensionality issues, like the total number of like record types in the record space that you're looking at. And so one of the first problems to mention is that we don't actually know what that dimensionality is. We have a pretty good idea, but the census form for 2020 hasn't been finalized yet. And so they may end up adding like 10 new questions onto the form that suddenly we have to account for in our process. Now that's pretty unlikely, but things could change between like what we expect based on what happened in 2010 versus looking forward to 2020. The major variables that we're kind of dealing with right now are age, sex, race / Hispanic, and this relationship to householder variable, which has values like you're the spouse of the householder, or you're a child of the householder, or a parent of the householder, and so forth. So the age range that we've been kind of using as a placeholder, the age range is one of the things that hasn't been finalized for 2020, but we've been using 0 to 115 as kind of a placeholder for that. Seems reasonable. I think that the oldest person alive right now is like 113 or 114 according to like a New York Post article. And so if that person's like still alive in a few years, then anyway. But 115 seems like a pretty reasonable estimate. Sex is male or female, so it's a binary variable. One of the changes actually going into 2020 is that race is likely going to include the Hispanic category. So in previous censuses, it was a separate variable, but incorporating it into race doesn't really change your dimensionality at all, but it's just something to be aware of. We have some major race categories. So in 2010, there were 6 of these: white, black, Asian, American Indian, Alaskan Native, Native Hawaiian, Pacific Islander, and then some other race category. Looking forward to 2020, like I said, these major race categories are also likely going to include the Hispanic variable, and also possibly an 8th category, which is Middle Eastern, North African. We also need to, so the PL94 table that I think Phil mentioned is the public law table that's used for redistricting, and that also includes combinations of these races. So we have to think about like someone that declares that they're white, black, and Native Hawaiian, for example. Relationship, looking forward to 2020, it's probably going to include either 19 or 20 different possibilities. So we think that our computational limits are reached somewhere around 3 million in terms of the solvers that we're using to do the post-processing and the DP algorithms that we're considering. And so the good news is kind of that in 2010, the dimensionality was around 500,000, and looking forward to plausible values for 2020, kind of worst case that we're looking at is this last possibility where we have 20 relationship values, we have the 2 binary sexes, and then there were 100, we're predicting around 116 different ages that you could declare, and then if you look at if you consider all the different combinations of races, then the race variable has 255 different possibilities. So that gives you a dimensionality just over 1 million, so that's kind of a good thing. We have some wiggle room if they do decide to throw in a new variable like eye color or whatever, that they say, oh, this is really important, we're going to collect that. But we don't have, but you know, we can't really do too much. beyond that. The real trouble shows up when we start looking at the SF1, the summary file 1 table. So if you parse through those tables, there's like a 300-page document or 400 pages or something that's public. You can go look at it, and if you only care about like low sensitivity queries, if you don't start thinking about the high sensitivity stuff, then there's about 14 key variables that we've identified parsing through that table for 2010. And I'm not going to read through all of them, but you have stuff in there, a lot of stuff about like the relationships and age ranges and things, whether or not children exist that are between like 0 and 6 years old, or children are present in a household between 7 and 17 or something like that. And so we have the 14 variables, so the bad news is that if you just kind of look at the Cartesian product of all those different variables, then the dimensionality that we have to deal with is something like 1.7 billion. That's a problem. That's not going to be tractable for our post-processing and DP. So the good news is that we have these structural zeros, which actually help us kind of alleviate this problem somewhat. So structural zero is, when we refer to that, is something that we're certain can't happen even before the data is collected. And there's really kind of three sources for these. One is that there's legal sources where these come from. There's logical sources. And then the third source is that before the data is handed to us, there's a team that does edits and imputation to the raw data, and we get handed clean data, so we don't have to worry about missing values in our process. We take this clean data as kind of like the truth. But what that means is that this edit and imputation team has certain rules that they put in place when they're processing the data, and we can't, when we generate our microdata, we can't reintroduce stuff that they declared to be not possible. So some examples of these things are that the householder and the spouse or partner of a householder has to be at least 15 years old. So anyone who's under 15, we can roll them out as being a householder. Children, siblings can't be over 90. Parents of the householder have to be at least 30 years old. And then another so most of these structural zeros somehow deal with age, is usually where they're coming from. But then another one is that, so we have 8 different binary race flags, and you have to have at least one of those checked. You can't have no race flags checked, and so that's why there's 255 combinations instead of 256 combinations that we have there. But then there's also structural zeros in households, like every householder can have exactly one. Every household can have exactly one householder. A child can't somehow magically be older than the householder. So these are that one's kind of logical. But then there's other ones that, like I said, are set by the edit and imputation team. So there's bounds on the age gap between a spouse and the householder that we have to respect, that aren't, it's not necessarily immediately obvious where those bounds come from, but it's something that they've said, we've studied this over the years, and spouses can't be more than 50 years apart or whatever. And so then we're like, okay, well then we have to make sure that the DP microdata that we generate doesn't violate that. And so so the question is, well, how much does this actually help? So the idea is that we want to be able to use this information and kind of reduce the dimensionality that we're dealing with. And so if you look at kind of the worst case scenario that we're considering for the demographic table, then you can start doing some computations and say, okay, well, if I take that structural zero that I mentioned that said that householders have to be at least 15 years old and spouses and partners have to be at least 15 years old, then how many, like, what am I able to cut out? And you do that, if you do that for all of the different structural zeros that we've been able to identify so far, and it's actually been quite the process trying to identify all of these different things, and lots of conversations with stakeholders within the Census Bureau. But so far we have about 200,000 of these. And so that's about an 18% reduction in the dimensionality for the demographic table. So that's kind of nice. We didn't actually, I mean, we were at 1 million. Our limit's 3 million, so we could already kind of handle it. But any reduction is kind of helpful. So looking at the reduction for the SF1 queries that we're considering, though. This is where it really kind of helps us a lot. So we started with a 1.7 billion approximation, and if you look at it conditioning on the household size, so a household that only has one person in it can't have a household type that says that there is a married couple living there, stuff like that. So by conditioning on the household size, you're able to drop the value down some, and then conditioning on interactions between these age variables. So age of own children is in some sense a subset of age of related children. So if you have a household that has an own child between 0 and 6 years old, then the related child variable has to also say that there's someone between 0 and 6 years old. So if you look at those interactions, then you get a bit more of a reduction. And if you combine everything that we've been able to think of so far, you get down to about 60 million. Yeah.
So we're looking at the number of possible different.
Yeah.
I'm confused when household gets mixed in. So when
Okay.
you're just looking are we looking at the number of possible different data records for a single individual, or for the household?
This is for queries that we've identified in the summary file 1, which kind of combines information from individuals and households.
I guess my question is, when you say dimensionality, this is dimensionality of the kind of intended output. I mean, I know the intended output is
right. Yeah. So yes. Yeah. That's yeah.
Okay. So all right.
Yes.
Dimensionality of the intended output vector.
Yes. Yeah. Do you want to make a comment, Phil?
I can also maybe further clarify here, Adam.
Yeah.
The 1.7 billion down to 60 million figures are strictly for household queries. They're not for queries that involve person-level data.
Okay. Yeah, that's right. Yes. Okay. So anyway, that's probably still not really going to be good enough. We have to. So this is a hard problem that we don't. I mean, the structural zeros help us some. They get us from 1.7 billion down to 60 million, but that's still not really tractable. And so we've got to figure out a way to handle it. So this is a big problem. If you have a solution, that would be awesome. Yeah.
Another problem that you want to have a consistency between people and households.
Yes. So that's Phil was talking about joins, and that's yes, that's another.
So it's kind of even if you manage to generate households, you're still not done.
Yes. Yeah. So it's a challenge. Yeah.
And just to understand the tables a bit better, so this household tables, we should think of one record in it for each. Suppose without privacy,
yeah.
The raw table would have one entry, one record for each household.
Yes.
And what would that record say about the people in that household?
So there is a family type variable that doesn't actually. I don't think I actually included it in the list here. But it says like whether or not it's like a household with a married couple in it, or a household with same-sex partners, or different information like that. And yeah, and you have the number of people.
Separately for each person in the household, the full demographic.
Right. You have some information. You have information about like how many children are in there, so that tells you something about the relationship variable that the individual persons have, and so there's connections. But yeah, it doesn't have like person records in there. It's one record with the household information.
But in the intended sort of final microdata, for each person, you would have like a household identifier.
Exactly. Yeah. And so there's this relational link between the people and the household. And that concludes my portion and so turn it over to Steve.
So now I'm going to talk to you about the geographic approaches we're going to take with this. But first I have to give you some acronyms so you can follow along with the rest of the presentation. First up we have the CUF, which is the CUF, which is the census unedited file. It is merely defined as the respondent data. Next we have the CEF, which is the census edited file, which is the data file after we have edited it. And then after that we have the microdata detail file, which we will be denoting in short by MDF, and that is the data file after disclosure controls have been applied to it. And then we have our DAS, which is the Disclosure Avoidance Subsystem, which is a subsystem used to preserve privacy of data while maintaining usability of data. Then we have the 18 E2ECT, which is short for the 2018 end-to-end census test. This is a test that is going to be used to prepare our decennial systems for the actual 2020 Decennial Census. So on this slide, we have the disclosure of...
Can you go back? Oh, good. Actually, this was my question. Your picture answered it. Thank you. Never mind.
Okay. Are there any other questions before I go on? Okay. So on this slide, we have the Disclosure Avoidance Subsystem process. This implements the privacy protections for our decennial census. It operates on the edited census records and is designed to make the census record safe to tabulate. So first off, we start with this census edited file, and then it's passed along to the Disclosure Avoidance Subsystem, and out from that process comes the microdata detail file for our 2020. So we want to preserve privacy of data with better techniques while maintaining data usability for our stakeholders. The legacy techniques that we have used before do not quantify the privacy loss inherent in publication releases. The new techniques which we're using differential privacy for allow measurable control of our privacy loss incurred in generating the microdata detail file from the census edited file. Our general approach for each geographic unit will be to generate differential privacy queries using the census edited file, and also to generate microdata that conforms closely to differential privacy query answers. We have a complex geographic hierarchy. We have 8 million blocks. We start with the nation, then we go down to state, county, tract, block group, and then finally block. We have sequential composition between each of these levels. And we also have parallel composition within. So we have the sequential between and the parallel within. There are two natural ways we can traverse this hierarchy. One is top-down. We can start with the nation and go down to the block. That is, we can go from the macrocosm to the microcosm. Or we can also go bottom up, the microcosm to the macrocosm in this case, which is the block up to the nation level. First, we're going to describe the top-down approach. The top-down approach starts with the national population and imputes the geography. We will first generate national differential privacy microdata. Then we take these differential privacy queries over the census edited file at the state level. We are going to assign national differential privacy people to states based on these queries, based on these state queries. And we're going to repeat this process ad infinitum down to all the way to the block level. So it's like a for loop in short, where we know how far we have to go. Then we have assignment to the lower levels of geography, and this must respect exactly known counts that we have given this process. We plan to use this approach for the final 2020 production run. But what about the 2018 end-to-end census test? Which,
Sorry, question. So the known counts are the like marginal counts or just the total counts per geographical unit?
So the three counts that we mostly have in mind here, I think, are the total number of householders, the total number of voting age persons, and the total number of non-voting age persons.
Got it.
There are a few others, but they don't really interact with those so much. So they're those particular marginals.
So you're not
But
generating,
not all the marginals.
you're not generating at the top level things about demographics and so on.
Well, so we are generating things about demographics at the national level. And it is important that at the state level, when you sum over all of the states, you must get the national level back again. So if that's the question that's being asked.
I see.
So there is an extra set of marginal constraints over the states that has to hold. And similarly for the lower levels of geography as you move on down.
so we will use the top-down approach for the final 2020 production run in short. But what about the 2018 end-to-end census test? What are we going to do about that? Well, we're going to try this bottom-up approach. We start with the block population, and we're going to aggregate up to the national level, i.e. rolling up. So first, we generate block differential privacy microdata using the geometric mechanism. Then we're going to post-process the block microdata to respect the invariance that goes on. We're going to then aggregate this to get block group differential privacy microdata, and then we're going to repeat this process rolling up all the way to the national level. We're going to use this approach for the 2018 end-to-end census test, which is going to generate response data only in the Providence, Rhode Island test area. So we're going to test it on a small test area and see what happens. So we have a bottleneck in all this. We have a notable bottleneck that goes on, which is post-processing. But post-processing is necessary to enforce invariance. We have quadratic programming and linear programming optimizers, which encounter numerical and runtime issues at histogram sizes around 3 million. We hope to leverage Spark to improve post-processing scalability. But the quadratic programming and linear programming algorithms are naturally sequential. We have some ideas for improving the scalability. One, we could imitate regression trees to decompose optimization problems. Two, we can imitate the branch and bound on total unimodularity linear programs with massive parallelism. That's a mouthful to say, but TUM stands for total unimodularity. Third, we can also do traditional decomposition techniques, like so-called Bender's technique. We still have a lot to go. We have a long ways to go. We plan to perform a bottom-up run for the end-to-end census test. We plan to perform a full top-down run on the public law 94 data, redistricting data workload using real data and simulated external data. We will also generate tools for stakeholders to get a better feel for how the differential privacy we implement, how it affects accuracy. We also plan to use Spark to scale differential privacy and post-processing methods to larger tables. And with that, that's the end of the presentation. Thank you for attending. Are there any questions? I saw you first.
A couple of questions around accuracy. So I guess there's two things I'm wondering about. One, you want to present this privacy accuracy trade-off curve to policymakers for them to make a decision, but you're faced with this kind of not precisely specified needs around accuracy that come from different stakeholders. So how do you imagine that working? And maybe a related, somewhat related thing is, are there expectations on how, even in the final products, you present the statistical uncertainty that is coming from the, I mean, you could say, okay, well, we publish the algorithms and therefore a statistician implicitly knows all the uncertainty that's there. But is there any expectation to produce something more easily interpretable than that?
So I think, Salil, the answer to the first question is murkier than the answer to the second question, but I'll start with the first one anyway. There is not really a clear vision for what the final weights and toggles are going to look like right now they're presented to leadership. My guess is it'll be something like we project down to just a few dimensions and something that we can present visually to them in a few dimensions at a time, and give them a toggle that will generate maybe a set of tables. They'll look at each of the set of tables and say, oh, this is how this particular subset of the workload's accuracy is varying with respect to the privacy budget we spent here. But it's a complicated problem in terms of sort of user interface, because that, as I think you're trying to highlight, there are more than just two parameters here. There's an unknown number of parameters because we're not even really sure what the ideal or correct decomposition of the workload is in order to accurately capture stakeholder concerns. I think we know probably at least two, but probably significantly larger than that. So largely an unsolved problem for the first question. The second question, I think the expectation is that we should be able to generate measures of uncertainty, the estimates of uncertainty that are implicit in the algorithms and in the DP infusion that we're providing in our final microdata. Originally, we were very concerned about that because we sort of have limited resources to make sure this all works. And when we first started working on the project, we were dealing with relatively complex data-dependent algorithms. And although they come with sort of asymptotic guarantees, some of them anyway, M1 in particular does, as I think you pointed out the other night, on worst case bounds, I don't think that those would have been necessarily very meaningful in practice at the scales we're working with. However, because we sort of accidentally worked our way away from data-dependent algorithms, just sort of by happenstance finding that data-independent algorithms substantially outperform them in our use case, I think now we may sort of have a path forward to generating the measures of uncertainty that are expected of us. So a naive approach that I've only really spent a few minutes thinking about, and we haven't actually tried to implement anything to attempt to do it yet, is just we can characterize the error distribution exactly for the full set of workload queries. We can sort of sample from that in some appropriate way. Having done so, then we can then sort of run a bootstrap over through all of our post-processing methods, and that should give us some measure of uncertainty at the other end of the process. But that was a very brief thought. If anyone has better ideas, we are certainly open to suggestions.
So question about privacy. Have you given any thoughts to using notions which are not pure differential privacy, like concentrated differential privacy, which kind of also has like this nice one parameter that like it's I think relatively easy to explain.
So it's funny that you asked that question, Ilya. Maybe not funny because it's sort of a natural question to ask. It actually occurred to me as I was walking into the room earlier today that I haven't had a conversation with Dan about that in quite a long time. And I don't recall what our reasoning was originally for going very, very closely to epsilon differential privacy. But there's certainly not like an organizational expectation that we stick to epsilon differential privacy. So it is possible that we may explore relaxations as we find that, if we find that the accuracy trade-off we're able to get here, the accuracy privacy trade-off is not acceptable.
So, there was a good reason not to use epsilon delta because of this delta.
Sorry, I need
delta
differential privacy.
Yeah, but as like we now have like a better intermediate definitions, I strongly encourage you to.
Yeah, especially for high dimensional. If you're looking at adding noise to these data independent mechanisms that you're just mentioning, they generally scale much better with the kind of number of outputs, which in your case is you convinced us is large.
Are there any particular concerns with just sort of treating so an alternative, like filling with concentrated differential privacy, for example, I'm just sliding it in a modular way and saying, hey, we were using geometric mechanism under standard differential privacy. I'm just jumping in and replacing that with a similar mechanism under concentrated differential privacy, or should all of the various composition theorems work out without my having to think about it too hard just right now?
They should work.
Okay, that's what I thought the answer was.
The appropriate composition theorem, meaning the ones for CDP or
Right, of course.
ESDP
Yeah.
or whatever.
Just
If I understood the question, the answer is yes.
I think you did, but thank you.
Yeah, just a quick follow-up on that. One of the issues is that policymakers have to be convinced to sign off on whatever's being done. And there's been a lot of effort going into getting them to buy into epsilon differential privacy, and it's not completed yet. To then go on and say, oh, well, we want something that's not quite the same, and to be able to explain it to them. Very high effort and very likely to derail things if they can get the utility, the accuracy, without doing so. At this point, to make that change, if it isn't absolutely necessary, it's going to be a real hard sell. So I think that's the main thing. It's an operational issue. We're not the community